In organic chemistry, converting an aniline into various functional groups is a critical skill. Today we explore two primary methods for replacing the diazonium group with halogens, the Sand-Maillard and Gattermann reactions, both essential for aromatic substitution. Directly replacing nitrogen gas from a diazonium salt requires a catalyst. While both reactions achieve the same goal, they differ in their reagents, efficiency, and reaction mechanisms. Let's break down how these two classic reactions compare. The Sand-Maillard reaction uses copper, i.e. salts, such as cuprous chloride or cuprous bromide. This method is highly efficient because the copper ion facilitates a radical transfer mechanism, making it the preferred choice for industrial applications. The Gattermann reaction is a modification of the Sand-Maillard process. Instead of using copper salts, it employs finely divided copper powder in the presence of a halogen acid. It is often considered a simpler but slightly less efficient alternative. Both reactions proceed via a radical mechanism. The copper source donates an electron to the diazonium cation, causing the release of nitrogen gas and the formation of a highly reactive aryl radical which then captures a halogen. When comparing the two, the Sand-Maillard reaction consistently provides higher yields. The use of preformed copper salts ensures a more controlled and complete reaction compared to the surface-level reaction of copper powder used in Gattermann's method. The primary difference lies in the catalyst. Sand-Maillard requires specific copper salts for each desired product, whereas Gattermann uses universal copper powder, with the specific halogen determined by the acid used, like HCl or HBr. To synthesize chlorobenzene using the Sand-Maillard method, we mix the diazonium salt with cuprous chloride in hydrochloric acid. The nitrogen bubbles away, leaving behind a pure sample of chlorobenzene in high yield. In the Gattermann approach for bromobenzene, we use copper powder and hydrobromic acid. While the reaction is easier to set up because copper powder is common, the lower yield makes it less favorable for large-scale production. A major advantage of the Sand-Maillard reaction is its ability to introduce the cyano group, CN, using copper isocyanide. This is a vital step in creating carboxylic acids and other complex aromatic derivatives. Temperature control is vital. The diazonium salt must be kept cold, but once the copper catalyst is added, the reaction proceeds at room temperature or with mild heating to drive off the nitrogen gas. The release of nitrogen gas is the thermodynamic driving force for both reactions. Because N2 is an exceptionally stable leaving group, the reaction is essentially irreversible once the nitrogen escapes the solution. If the reaction is too slow or the temperature is too high, water can act as a nucleophile, creating phenol as an impurity. This is why the efficient radical pathway of the Sand-Maillard reaction is so valuable. In the Gattermann reaction, the copper powder actually reacts with the acid to produce small amounts of copper ions in situ. This explains why it is essentially a slower, less concentrated version of the Sand-Maillard reaction. To summarize, Sand-Maillard uses copper salts and gives higher yields. Gattermann uses copper powder and is easier to perform but less efficient. Both are radical-based substitutions of the diazonium group. Remember that the choice between these reactions depends on your need for efficiency versus reagent availability. In most laboratory settings, the Sand-Maillard reaction remains the gold standard for these transformations. Test your knowledge: which reagent is used in a Gattermann reaction to produce chlorobenzene? If you chose copper powder with hydrochloric acid, you are correct. Copper salts are reserved for the Sand-Maillard method. Understanding these substitution pathways allows you to build complex molecules from simple aniline precursors. Keep practicing these mechanisms to master organic synthesis. Generated by Vision Solve AI.